In this video, we're looking at stochastic dynamic programming, which we denote sometimes as CDP. In deterministic dynamic programming, the state variable evolves according to the difference equation given here. This is the state variable, and this is the control variable, u of t. It's the control variable that we choose over time. We choose that ut. So what we're going to do here that's different than what we've done before is that we're going to let xt be random or stochastic. So that xt evolves along this equation, where this component here is your random variable. In practice, this equation is often represented by a transition matrix for each of the controls, and often we refer to this stochastic dynamic programming as Markov chain programming, but only in the case where the difference is from one period to the next. In other words, all of the information, which is why it's Markov, is contained at time t minus 1. So when we come to time t, all the information that we have is available up to t minus 1. So we can't go back to t minus 2, or in this case, we're looking, all the information is available at time t plus 1. All we have is that this t here is where all the information is found. Nothing is found at t minus 1. The flow chart for stochastic dynamic programming is very similar to that for non-stochastic programming. The only difference here is that this error term enters in, these E1, E2, E3, etc., which is the random effect that occurs at any particular stage. So x1 is our state variable, so let's say the population of fish, and we now enter that stage. We make a decision, U1, to fish them and how much to take, for example. Harvest would be an example, and we get a return R1. That then, along with this random variable, determines the level of x2. Then given x2, again, we have a decision we make whether or not to harvest and how much to harvest, given by U2. And then going to the next stage, to x3, we have this random effect. And of course, we're going to get out this fixed return R2. And so on all the way out to this terminal value here. Now, what's interesting with stochastic dynamic programming, just as it is with non-stochastic dynamic programming, is that we start at the terminal value. We start our method for solving these kind of problems by beginning at the terminal value. Now we're going to motivate this with an example from Buongiorno and Gillis, Decision Methods in Forest Management. And it's actually a bad example in some ways, but you'll have to put up with it. So what we've got is 3 states, low, medium, and high, and these refer to the amount of volume on a stand of timber. So if it's less than 400 cubic meters per hectare, it has low volume. If it has high volume, it's greater than 700 cubic meters per hectare. Now, to give you some context, boreal forests rarely exceed 250 cubic meters per hectare. Interior forests in British Columbia rarely exceed 500. And it's only these coastal forests that exceed that, and they top out at around 1,200 cubic meters per hectare. So if you're looking at a coastal forest, a rainforest with the huge trees, then you'll get up to that kind of a measure. Otherwise, you're lucky to get 250 cubic meters per hectare on trees in northern Alberta, for example. It's more like 160 cubic meters per hectare than it is 250. Now, in this forest management example, we're going to start with the transition probability matrix when there's no management. And when there's no management, then we determine this to be, so if you're in the low state to begin with, so let's say you're at 200 cubic meters per hectare, and the chances of staying there is 40%, and the chance of going to the medium, the higher state, is 60%. Now notice that the assumed time step is 20 years, so that's a fairly large period of time, but then remember, trees don't grow that fast, and most models that we deal with in forest management use a 10 period time step. So even models that the BC government is using and so on generally have a time step of 10 years. If you go to an annual time step, it becomes extremely difficult to manage any kind of models of forest management. I've done that in the past, but we had to use a supercomputer to do an annual problem that normally would be easily solved on a regular computer using a 10 period or a 10-year time step. So here we have, again, as I mentioned, if you're in a low state, there's a 40% chance that you stay there, 60% chance that you move to the higher state, M. If you start in an M, in a medium state, there's a 30% chance you stay there, 70% that you go up. And likewise, if you're in a high state, there's a 5% chance that you drop back to a low state, 5% that you drop back to a medium state, well, generally as a result of such things as wildfire or pine beetle or something like that. And there's a 90% chance that you stay there. Assume that the forest is initially in state L, low state, and that its probability of being there at that point is 1. So we want to know how it moves over time without management. So how does this forest evolve over time without any management, and where will it end up? So we begin with P0, 1, so 100% chance that you're in the low state, 0 that you're in a medium or high state. So what we do is we multiply that vector by this transition matrix, this probability transition matrix, and notice that we get 0.460. So we actually get that back. Then we take that value and we multiply it again by this same matrix, this transition probability matrix, and now we get 0.164242. So 16%, 42% we're in a middle state, 42% we're in a low state. And we keep doing this according to this equation here, this equation, this one here, and we do that for a large number of periods, and what we end up with is that there's at any given time that there's a 7% chance that that forest that started in that low state, that after a large number of years have passed, is still in that low state. 7% probability, 12% probability that it's in the medium state, and an 82% probability that it's in the high state. And of course, this has to do with things like wildfire and beetles and other kinds of natural disturbance. So in the long run, the stand of trees will have more than 700 cubic meters of timber on it with probability 82%, and 400 to 700 cubic meters with probability 12%. How long can one expect the stand to remain in any one of these three categories? We refer to this as the mean residence time, and we calculate it using this formula here, where MI is the mean resident time of staying in state I. So either low, medium, or high. So I equals low, medium, or high. SL is the stage length of 20 years. PII is the diagonal element on that matrix that we had above, or the probability that a stand is in state I at the beginning of the period and is still in state I at the end of the period. We also can calculate a mean resident time, the mean resident time here, and that's given by the average of that. Well, that's basically determined by that formula MI, and we find that there's a 33 years that it will be in the low state, 28 years that it's going to be in the medium state, and that it stays in the high state for 200 years. So even for old growth forests, because these numbers aren't, I mean, they're contrived, but they're somewhat realistic because these are two forest management people and economists who are looking at these. But it shows you that even for old growth forests like we find on the west coast here, and particularly on Vancouver Island, but also up coast a little bit on the mainland, these forests eventually decay. They eventually fall apart. For example, the argument has been that sawmills are not cutting trees, or they're cutting big trees and they're taking those big trees and basically chipping them and making them into pulp rather than timber. And the reason is, if you consider this to be a tree, all right, and this is the ground, and if you top that tree for whatever reason, maybe through wind blow or something like that, the water gets in here and it rots the inside of the tree out. And the whole tree then it might look fantastic and like a huge tree, but in effect, the inside of the tree is all mush. And thereby, when it's cut, the only good use that it can be put to is as pulp. Now, we also define the mean recurrence time as MII as being equal to the stage length divided by probability that comes from that long run probability which we calculated, this one here, in an earlier slide. So it's the time that it takes for a stand in state I to return to state I after exiting it. So the mean recurrence time for a low state is 285.7 years. For a medium state, it's 166.7 years, and it's only 24.4 years for the high level of timber on the site. Now, we need to have something to do with management. The mean residence time, doing the same as above, we can easily find for the low states 28.6 years, 26.7 for the medium, and 20 years for the high state. We can calculate these probabilities of being there as before and the mean recurrence times as well, all right, using these formulas down here. So calculating the long run returns, suppose we have the following immediate returns from harvest under management. Let's say that if you went to harvest the timber and it was in a low state, you wouldn't earn any money. Suppose that it was in a high state, you'd not earn any money. And if it was, in a medium state, you wouldn't earn any money, but you would in a high state. So that means that the person managing or owning this land would always harvest the trees once they reach that high state. We're going to look at that in a little bit more detail later on. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.